All right, so welcome to our last lecture. Today's lecture is on induction, and it's a little bit different from all the previous lectures in the sense that we're teaching you a way to prove rather than some basic concepts. So induction is often compared to toppling over a row of dominoes because when you tip over the first domino, then all the dominoes after will tip over if they are close enough to each other, and eventually all the dominoes will fall. So a typical induction argument will consist of two parts, and these two parts are called the base case and the inductive step and hypothesis. So the base case is like the first domino in a domino analogy, and this is usually um, n sub 0, which basically the base case number is with 0 or 1. But on the other hand, it could also be not 0 or 1. It just depends case by case, but most often it's 0 or 1. Now, assuming that now after verifying the base case, you assume that that it holds true, the statement holds true for some arbitrary value of k. So p of k is true. And then you use that to prove that p of k plus 1 is true. And this is called the inductive step. The assumption that p of k is true is called the inductive hypothesis. Now, the reason that this works is if you have like a base case that you prove is right, then you can repeatedly apply the second part, assuming that's right too, and then you can induct all the way to infinity, in which case you would be proving it for all natural numbers. So if you are considering induction, you should also always first check if there is a reasonable way of linking up p of k to p of k plus 1. So making sure that consecutive cases have some way a relation to each other. Now there are two major types of induction. Um, so the premise of induction is that you prove this proposition p of n, and then you also know that p of 0 is true, and that given p of n plus 1 follows. So that's basically a more advanced way of saying what I said in the introduction. And then, so in this domino effect, you get that for all k is greater than or equal to 0, p of k holds true. And this is called the weak principle of induction, in which you only assume the base case is true, and then you perform the inductive hypothesis and then the inductive step. And then generally, you use it to prove a statement over natural numbers, but this is not always the case, but it's most often the case. And then there is some relationship between consecutive terms, as I mentioned before. So there are several manipulations that can be made. So we can start with a base case that's non-zero, as long as it's true, obviously. And then we prove the statement for all k that's greater than or equal to the base case. We can also change the inductive step. So instead of saying consecutive in the sense that it's n plus 1, we can show that p of n plus k. And then, but that means that for the base case, we have to account for everything from 0 to k minus 1, or 1 through k, depending on when you start. And this is useful for proving statements over multiples of k. Yeah, sure, you can go. But also, of course, this means that we will have to consider a different form of base case, as I mentioned. So yeah, we'd have to group them 1 through k or 0 through k minus 1 because you're incrementing by k instead of 1. Now, we can also strengthen our inductive hypothesis by assuming not only p sub n, but p sub n minus 1, p sub n minus 2, etc., to show p of n plus 1, given that we are able to show p sub 0 through p sub k. Now, this is basically the principle for the next type of induction that we talk about, and it's called strong induction. So this offers a few advantages over the weak principle of induction. So first of all, we only need to prove the base case, and the inductive argument to prove the inductive statement. So because P sub 1 follows from P sub 0, etc., we have much more power to prove our inductive argument. Because remember that before, the inductive hypothesis meant that we only had that P of K was correct, the base case was correct, and also that, and then we had to use those two statements to prove P of K plus 1. But in this case, we have P sub 0 is correct, P sub 1 is correct, all the way to P sub K is correct. And then we can use all of those K plus 1 statements to try to prove that P of K plus 1 follows. So there are other ways to perform induction other than strong induction. So for example, there's Cauchy induction, which uses like multiplying by 2 and subtracting 1, stuff like that. So, but for the cases that we are dealing with, we will only focus on the basic weak and strong induction and none of the weird inductions. So let's do a simple example. This is one of the most classic examples of induction. So we want to prove that 1 plus 2 plus all the way to n is equal to n times n plus 1 over 2 for all positive integers n. Now, what we do is we can use the induction, right? So we want to show it for all positive integers n, which suggests that the base case should be 1. So let's do the base case first. I'll abbreviate it BC. All right. So n equals 1. Obviously the left-hand side is equal to 1 because the sum from 1 to 1 is 1. And the right-hand side is also equal to 1. Our right-hand side is 1 times 2 over 2, which is 1. Right, so obviously the base case holds. Right, the base case has been proven. Now, what you do is you want to assume that this result holds for some integer k. So we assume this is the inductive hypothesis, right? We assume this, and I'll abbreviate it IH. So if we assume the inductive hypothesis, which is that the sum of the numbers 1 through k is equal to k times k plus 1 over 2, and now we confirm the inductive step. So the inductive step means that given the inductive hypothesis, how can we prove that how can we prove that P of k plus 1 is true? Well, if we add k plus 1 to both sides, we would get that 1 plus 2 plus k plus 1 is equal to k over 2 plus 1 times k plus 1. And this is then equal to k plus 2 over 2 times k plus 1, which is then equal to k plus 1 times k plus 1 plus 1, which is equal to p of k plus 1, right? So if we go back to our beginning statement, we notice that all we did was we added k plus 1 to both sides from the inductive hypothesis. Now we assume the inductive hypothesis is true because of the weak principle of induction, right? And then after adding k plus 1 to both sides, we realize that we have formed the statement for, we try to form the statement for a piece of sub k sub k plus 1, because we know that it necessarily is true because of the assumption that P of k is true, which is just that 1 plus 2 all the way to k is equal to k times k plus 1 over 2. And then we only performed valid operations, right? We didn't use any other techniques except some basic algebraic manipulation. So we can know that this is true. So that, in other words, once we get that 1 plus 2 plus all the way to k plus 1 is equal to k plus 1 times k plus 1 over 2, then we have proved the statement for k plus 1 as well. So after you get the statements for k plus 1, and the base case, then you're essentially done with the problem. This is not like a formal write-up type of thing. If you want to learn how to do proof writing, I recommend you just practice and then you can read sample proof solutions. Here we will only be providing a rough sketch of the proof. So in an actual proof, you would have to write more words, obviously, and then explain your thought process a little bit more. All right. Yeah. For the second problem, I picked something that is pretty similar to the first one, right? So the first problem was adding just the natural numbers themselves. This one is adding the squares of these numbers. And this formula is pretty well known. So if you don't, you should probably memorize it if you want to go on to doing comparative math. But for today's lecture, we will just be trying to prove the statement. So it says, show that what the sum of the squares, so 1 squared plus 2 squared all the way to n squared, is equal to n times n plus 1 times 2n plus 1 all over 6. So once again, we want to start with the base case, right? So the base case would be that n equals 1, right? Because it's positive integers. If it said all for non-negative integers, you might want to start from 0 because you would have to prove from 0 through n rather than 1 through infinity, right? So the base case, we have n equals 1, and we can verify that 1 squared is equal to 1 times 2 times 2 plus 1 over 6, right? Which is 1, right? Both sides are equal to 1, so the base case holds true. Next, what we want to do is write out the inductive hypothesis, right? So the inductive hypothesis is assuming that k is true. So 1 squared plus k squared is equal to k times k plus 1 times 2k plus 1 all over 6. And then finally, we want to perform the inductive step, right? So in order to do this, we want to add, sorry, excuse me. We want to add k plus 1 squared to both sides, right? So we would get 1 squared plus k squared plus k plus 1 squared, right? We want to keep the left-hand side in the same format. And then we would add k plus 1 squared to the other side as well. And then let's just focus on the right-hand side now. So on the right-hand side, we have, I'll use a different color. So on the right-hand side, we have k times k plus 1 times 2k plus 1 all over 6 plus k plus 1 squared. And now we can factor k plus 1 out of this expression to get k plus 1 multiplied by k times 2k plus 1 all over 6 plus k plus 1. And then from here on out, we can write this is k plus 1 times 2k squared, right? We'll expand the expression, 2k squared plus k, and then plus 6k plus 6 all over 6, right? And then we can factor this to be equal to k plus 1 times 2k squared plus 7k plus 6 over 6. And then we can finally conclude that this is equal to k plus 1 times k plus 2 plus times 2k plus 3. And we get that just from factoring the quadratic. Expression here is the 2k squared plus 7k plus 6. And you should get really good at factoring these types of quadratics. But yeah, that's the factorization for the quadratic. So this side is the factorization for this quadratic, right? And then this is log over 6. And then we can rewrite this expression as follows, right? So we can have k plus 1 times k plus 1 plus 1 times 2 k plus 1 plus 1 over 6. And as you can see, this follows this expression here, right? This expression here follows the same format as this expression, right? Except instead of k, we replaced k with k plus 1. So in other words, we have effectively proven, right? Because if we follow the line of equality, we go from here to here, and then we go down, right? So that means that 1 squared plus k squared plus all the way to k plus 1 squared is equal to k plus 1 times k plus 1 plus 1 times 2 times k plus 1 plus 1 all over 6. So that means we have proved effectively we have effectively performed the inductive step, right? And shown that P of k plus 1 is true, right? Right. And then by the weak principle of induction, we have effectively proven that because we have a base case, we had an inductive hypothesis, and now we have the inductive step. So by the infinitely long domino chain effect, we have that the statement is effectively proven by induction, right? And I'll zoom in on the formula again, because this is a pretty important formula. And basically all of the sums can be proven this way. So we proved like regular sums, right? This is regular sums. We proved sums of squares. And then there's also formulas for the sum of cubes, right? Right? There's also, and there's many more, right? But effectively you can prove if they ask you to prove the closed form of some form of sum of cubes, sum of squares, sum of regular, sum of fourth powers, whatever, you can almost always use induction. Although it will get more ugly as the powers get higher because you will need to expand more. All right, so let's do a different example. So determine with proof the maximal possible number of regions in which the plane can be partitioned with the end lines. Now, Atreya tackled this problem using recursion. And you'll notice a very key similarity between recursion and induction, because recursion, you use the previous example, and then you apply some sort of manipulation for each individual case, but the manipulation is always the same to get the next value, right? But induction, it's basically the same thing, right? You manipulate the previous expression to get um the to prove that the next expression is true, and then you would prove that the next expression is true, so on, so on, so on forth, right? And I believe that in the lecture, so since Threa already came up with a formula for or rather the recursion for it, I will not be drawing out examples, but I will just include a table of values, right? So if you have, this is number of lines, right? And this is regions, right? So with one line, obviously you have 2. With 2 lines, you have 4. With 3 lines, you have 7. With 4 lines, you have 11. And 5 lines, you have 16. Right? I will just briefly go over this problem because Andrea already went over the basic gist of solving it. So basically, how you would do this problem is you would have the base case is n equals 1, right? And that's obviously true. Oh wait, sorry, I should probably mention what the closed form expression is. You notice that this is just 1 greater than the triangular numbers, right? If we have the triangular numbers, which is the sum of where the nth triangular number is the sum of the integers from 1 through n. the triangle numbers would be 1, 3, 6, 10, 15. So notice that the regions are just one greater than that. So that means the closed form expression here is k times k plus 1 all over 2, right? And then plus 1, right? So effectively, we can use the base case, and you would get that you get 2 equals 2, right? The number of regions is 2, and if you plug 1 into this formula here, you would get that the right-hand side is also 2. And then you would have the inductive step, right? The inductive step would be assuming for some k, for some arbitrary k, as they would say, you would have that the number of regions of k is equal to k times k plus 1 over 2 plus 1. And then you want to perform the inductive step, right? So the inductive step is basically, it's pretty basic. So what you would have is, remember that this is 1 plus k and then plus 1, right? And then we can use the result from the triangle numbers. So recall that in the previous lecture, Adrea mentioned that you don't want to have more than 2 lines intersecting at the same point. And moreover, each intersection with a line will form another well, when we draw the line k plus 1, we wanted to intersect other lines as much as possible, right? To form as many regions as possible. Because since we don't want more than one line intersecting at the same, more than 2 lines intersecting at the same point. So that'll give us k distinct intersection points. And this will divide the line into k plus 1 segments. And then each of those segments will divide a previous region into 2 new regions. So the number of regions is now, so the regions for, sorry, this is an R. The regions for k plus 1 is equal to 1 plus k, so all the original regions. And this new line forms k plus 1 regions, right? Right? And then this will be just k plus 1 times k plus k plus 1 times k plus 2 all over 2 plus 1. And this just concludes the problem, because clearly we had the inductive step, and then we had the inductive, we used the inductive, sorry, this is the, I made a mistake here. This is the inductive hypothesis, right? And then this is the inductive step, right? So yeah, this is just a rough sketch of the recursion problem mentioned before, mentioned in Adrea's lecture. But rather than using recursion, we came up with a closed form expression, and then we used sort of like the concept of recursion to prove the statement using induction. All right, let's do more problems. So these problems are gradually getting a lot more difficult. So we want to prove that for any natural number n is greater than or equal to 2, right? So this should give us the hint that we want to start with the base case of 2. And obviously we can only start with the base case of 2 because it doesn't give us the example for 1, right? And then next we want to prove that 1 over 2 squared plus 1 over 3 squared plus all the reciprocals of the squares is less than 1, right? And this essentially sets a bound as well for the following expression. This is just an interesting comment. It has nothing to do with the actual proof, right? So, so 1 over 1 squared plus 1 over 2 squared, the infinite series to 1 over infinity squared, right? That's not how you would actually write. You would write a limit, right? But what is this equal to, right? Well, this would help set a bound, right? Because if this is true, then 1 plus 1 over 1 squared plus 1 over 2 squared this would be less than 2. And then we could bound it saying that this expression here would be less than 2 as well. For the curious listener, the sum of the reciprocals of the squares is pi squared over 6, which you will notice is indeed less than 2, right? Because pi squared is about, let's say about roughly 10, right? And then over 6, so that's clearly less than 2. Pi squared is also less than 10. So, all right, so that was just a side tangent. Now let's go back to the original problem. Right. So let's start with the base case, right? For the base case, we have that, of course, 1 over 2 squared. Actually, that is not how you want to solve the problem. How would you want to solve this problem? Okay, so let's try this. So let's first not prove the statement, as surprising as that may sound. Instead, let's focus on a different statement. We want to prove that 1 over 1 times 2 plus 1 over 2 times 3 plus all the way to 1 over n minus 1 times n is equal to n minus 1 over n. And notice that if this is true, then this necessarily follows. Well, why? This is because we know that 1 over 2 squared is going to be less than 1 over 1 times 2, because 1 times 2 is always less than 2 squared, and similarly 2 times 3 is less than 3 squared. So this value is strictly greater than this. This value is strictly greater than this, right? This is greater than, this is greater than. And if we match all these terms together, they're all greater than. And they're all strictly greater than as well, right? So now what we can prove is, if we can prove this statement is true, we will know that the above statement is true. And now you'll notice that, sorry, now you notice that induction does not always take on the form of proving the statement the problem gives you, right? If I tried to induct on just the problem statement alone, I will not have been able to. Sorry, my nose is a bit congested. Give me a second. Sorry about that. Right. So if we try to induct on this on the problem statement given, we will not have been able to induct in the same in an effective manner to be able to prove that it's less than 1. But by coming up with a statement that, if proven, will prove the problem statement, then this statement can be proven by induction. This is much easier for us, right? So we can prove this statement with induction, but what I want to show you guys instead today is something that's, I guess you could say, closely related to induction. In this sense, you can prove this statement using induction, but this is not technically induction, but it's something pretty related to it, in the sense that it's very similar, because you are adding consecutive cases and then you're basically canceling stuff out, right? Instead of like trying to prove the next statement. And because this type of canceling out is very useful, because this is called like a telescoping series, because right, so, and I'll show you what this looks like, instead of just talking about it. So 1 times 1 plus 2 1 over 1 times 2 can be written as 1 over 1 minus 1 over 2, right? Because this is 2 minus 1 over 1 times 2, which is 1 over 1 times 2, right? And then 1 over 2 times 3 can be written as 1 over 2 minus 1 over 3, which is equal to, and then so on and so forth, right? So finally, 1 over n minus 1 minus 1 over n is equal to 1 over 2 times, sorry, 1 over n minus 1 times n, right? And then what you can notice that if you add all of these expressions together, right? If you add all of these expressions together, you would have that the 1/2s cancel out. And then this would cancel out, etc., right? And then you would have 1 over 1 minus 1 over n, which is n minus 1 over n, right? And you can see why this is so powerful, right? Because obviously, let's say you wanted to evaluate 1 over 1 times 2 plus 1 over 2 times 3, all the way to, say, 1 over 9 times 10. Well, if you didn't know about this telescoping sequence, then you would have had to add 1/2 plus 1/6, etc., and then you have to like find a least common denominator, and you would have to convert those fractions to the least common denominator, and then would add them again, right? But with the power of telescoping series, you can write these fractions into a different form of expression, and then when you add them, you find that there's some nice cancellation that's happening, right? Because whenever 1 times 2, then minus 1/2 from that decomposition, and 1/2 from the decomposition of 1 over 6, they cancel out, right? And this is called telescoping, probably because it has this sort of like infinite cancellation type of thing, right? I don't know how to better describe it, but in a sense, this is called pretty sure it's just called telescoping series. But in this case, it's always just you have some very nice cancellation going on, in the sense that when you come up with a final expression, the final expression is pretty elegant, right? So if we go back to our original problem statement, we see that this is pretty elegant. Now, another way that we could show this, instead of using telescoping series, is basically induction, right? You would just have a base case. You would have a base case that 1 over 1 times 2 is equal to 2 minus 1 over 2, which is obviously true. And then you would perform the inductive step. You would have, an inductive hypothesis that would be like 1 over 1 plus 2, 1 over 1 times 2, all the way to 1 over k minus 1 times k is equal to k minus 1 over k. And then you would try to prove that what you want to prove that is that 1 over 1 times 2 plus all the way to 1 over k times k plus 1 is equal to k over k plus 1, right? And obviously what you could just do is add 1 over k over times k plus 1 to both sides, right? Because you can simply do that and you would get the answer. But I find that I think the idea that you can use these telescoping series instead to prove this statement is more elegant than using induction, because the everything on the left side here, right? All of this does not require many words. But when you write an inductive proof, you have to go through and explain, right? You have to explain what the base case is. You would have to explain the inductive hypothesis. You would have to explain the inductive step. But here you can use simple algebraic manipulation. Like you can just say, I rewrote the fraction as follows, and then it telescoped, or in more simpler terms, I think on a proof I would write it telescoped, but to explain it better, you could say it simply canceled out. Right, everything canceled out pretty nicely to get this expression. So this is one case where we can use telescoping series I'm not sure if telescoping fractions is the name, but I think it's a name. Um, to prove a statement. And this is another thing, right? Because I talked about this at the beginning of the problem, but we can see how helpful that changing the problem statement was towards solving this problem, right? Don't always get too fixated on what the problem is trying to prove. Think about other statements that would imply the statement, the, the problem. So if we call the problem proof statement A, so this 1 over 2 squared plus all the way to 1 over n squared less than 1, if we have difficulties trying to prove the statement just by itself, then we might want to think about, well, what other statements B or C or D can imply that A is true, right? So in this case, we found that 1 over 1 times 2 plus 1 over 2 times 3 plus all the way to 1 over n minus 1 times n would, if we find this expression to be equal to n minus 1 over n, which is clearly less than 1, is true, then we can definitely prove that then the problem statement itself, A, will follow, right? And it was also much easier to prove, right? You can solve it with induction, with telescoping, with whatever, right? Now let's do something, now let's try to prove a statement called Bernoulli's inequality by induction. So let n be a positive integer and let x is greater than or equal to -1, right? Show that 1 plus x to the power of n is greater than or equal to 1 plus n times x. So for the base case, right? Well, first let's see, right? What should we induct on, right? Because there are two variables in this problem. There's n and there's x. So a big hint here is that n is a positive integer, whereas x is simply any number that's greater than or equal to -1. And it's much easier to induct over the integers than it is to over x, right? Because x doesn't have any restrictions except that it's greater than or equal to -1. But n has restrictions. It has to be a positive integer, right? So the base case here would be n equals 1 because it's positive integer, not non-negative integers, right? So n equals 1, we would get that. Well, if you notice, n equals 0 works as well because the left-hand side would be 0 and the right-hand side would also be 0. Sorry, the left-hand side would be 1 because any number raised to the 0th power is 1 and the right-hand side would also be equal to 1. That's just a side note, but we have the base case that n is equal to 1. Right, so the given equality would become 1 plus x is greater than or equal to 1 plus x. Right, and this is clearly true, right? Because, well, 1 plus x is equal to 1 plus x, right? Now, just by the commutative property, right? Right, not the commutative property, the I forgot what it's called, the identity property, or yeah, but just like it's equal to itself basically. But we will prove this. Now we have the inductive step, right? So let's assume that for some, okay, predictive hypothesis, sorry. So for some n equals k, we have that 1 plus x to the k is greater than or equal to 1 plus kx. Now, what about 1 plus, right? And then we have the inductive step. So let's first write out what we want to prove, right? So what do we want to prove? We want to prove, let's write this in a different color. So we want to prove that 1 plus x to the k plus 1 power, right? This is greater than or equal to 1 plus k plus 1 times x. Okay, and now we can get started, right? So we have that, what we can do is we can multiply both sides by k plus, by what, x plus 1, right? And we know we can do this. Why? Because we mentioned that above that x is greater than or equal to -1. it's commonly known that if you multiply an inequality, both sides of an inequality by a negative number, you would have to flip the direction of the inequality. But in this case, we don't have to worry about that because the problem mentioned that x is greater than or equal to -1. And the fact that it mentioned it is also a big hint that you might be multiplying the inequality by x plus 1, right? So anyway, if we multiply both sides of the inequality by x plus 1, we would get 1 plus x to the k plus 1, right, is greater than or equal to 1 plus kx times 1 plus x, which is equal to 1 plus k plus 1x plus plus kx squared, right? But we know that kx squared is this expression is um greater than 0, right? Why? Because well, it's greater than or equal to 0, right? Because x squared is greater than or equal to 0. And remember that k is essentially a positive integer as well. So k is a positive integer and x squared is non-negative. So that means this expression here is non-negative as well. Kx squared is non-negative as well. So that means this expression here is greater than 1 plus k plus 1 times x. Right, and then we'll notice, hey, we proved what we wanted to prove, right? Because the left-hand side is this here, and the right-hand side is this, right? Well, we multiply both sides by 1 plus x, and we actually proved something even better than what we had before, right? Right, this is greater than equal to, not greater than, because kx squared can be 0 if x is 0. So yeah, you would notice that we've proved this problem. And, you know, it looks pretty intimidating at first, but you're like, well, there's an exponent, so it's going to be a little bit more difficult, and there's also 2 variables. But the first thing we did is we pinpointed which variable we want to perform induction on. In this case, it was n. And then we just did the same thing as before, right? We set up a base case, we did an inductive hypothesis, and then we performed an inductive step. It's generally a good idea, I think, for me, at least, that we write out what we want to prove before we actually perform all the algebraic manipulation, or if it's like a combo problem, there's sometimes induction for combo problems as well. So like the n lines type of thing. I always try to write out like, what do I want to prove first, and then what type of manipulations can I do to get from the inductive hypothesis to what I want to prove. All right. We have 4 more examples, but I don't think we'll be able to get through all of them. All right, so this is example 3.6 for Mott's Little theorem. So this theorem also comes up pretty often. So let P be a prime number, and let us prove that n to the p minus n is divisible by p for all positive integers n. There's other ways to write this, which is basically, we also have that the other way to write this is commonly, if you recall our lecture on modular arithmetic, it's that n to the p is n mod p, and this also implies that n to the p minus 1 is 1 mod p, right? But yeah, this is basically how Fermat's Little theorem is generally used. Now let's try to prove it, right? So let p be a prime number, prove that n to the p minus n is divisible by p for all positive integers n. Once again, we have 2 variables, right? We have p, which is the prime number, and we have n, all positive integers. So we want to induct over n. Why? Because p, the primes, don't have any sort of like significant relationship between them, at least as far as our mathematics knows. But positive integers do, right? From the first positive integer to the next, it would just add 1, right? So that's a lot easier for us to deal with. So let's do with the base case, right? So the base case, we have n equals 0, n equals 1, sorry. And obviously 1 to the p minus 1 is 0, which is divisible by p, right? 0 is divisible by everything, right? Except for 0, but you don't divide by 0 in the first place. All right, so next we do have the inductive hypothesis, which we have that assuming that n equals k works, right? So inductive hypothesis, n equals k, we have that n to the p, we have k to the p minus k is equal to 0. Is divisible by, well, 0 mod p. Let's put it that way. Okay, sorry, let me replace this n. Okay. Right, and then let's do the inductive step now. Now let's do what we did before, right? So what do we want to prove, right? So what do we want to prove? We want to prove that this one's more straightforward. We want to prove that k plus 1 to the p minus k plus 1 is equal to 0 mod p as well, right? And what we can do here is we can use the binomial theorem, right? Recall I think in the very first lecture, I mentioned the binomial theorem, which is a way to expand binomials. So let's expand this binomial, right? This binomial here, right? So this one, if we expand the left-hand side, we would get k to the p plus p choose 1 times k to the p minus 1 times plus p choose 2 times k to the p minus 2 all the way to p choose 1 times k plus 1, right? No, p minus 1, sorry. P minus 1 times k plus 1 minus k minus 1. Now, we notice that, first of all, we know that k to the p minus k is 0 mod p by the inductive hypothesis. So we can cancel these two out, right? Because this is going to be 0 mod p from the inductive hypothesis, right? Now next, the ones cancel, right? So this conveniently cancels here. And then each of these coefficients here, so p choose 1, p choose 2, p choose 3, etc., is divisible by p, right? Well, how do we show this? Well, p choose I, so this is binomial notation, a review, right? So p choose I is equal to p factorial over I factorial times p minus I factorial, right? Now p is prime, right? So p factorial contains a factor of p, right? This is a factor of p. This does not have a factor of p, right? Because just by the definition of a prime, its only factors are 1 in itself. So if there was a factor of p in I factorial, p would not be a prime. And the same thing occurs for p minus 1 factorial, because I and p minus 1 are both strictly less than p. And there are no multiples of p, there are no positive multiples of p less than itself, right? Or positive divisors of p other than 1 in itself. So that means that this is 0 mod p, this is 0 mod p, everything in the middle is 0 mod p, this is 0 mod p, right? So everything here comes out to be equal to 0 mod p, right? Which is what we wanted. So this isn't a very rigorous proof, clearly, because there's a lot of stuff to be filled in the middle. There's some explaining to do why this works, etc. when you write a formal proof. But this is a rough sketch, right? You induct on the n, rather than p. So that's the first step. The base case would be n equals 1 because we want to induct over the positive integers. And then the inductive hypothesis, we assume that it's true for some n. And then we use the inductive step, we use the binomial theorem. So you would have to know the binomial theorem for this problem to prove that this is indeed equal, that k plus 1 to the p minus k plus 1 is also equal to 0 mod p. And then we can use the weak principle of induction to show that, well, this is true. All right. Let's try to do this problem. I don't know if we have enough time though. All right. So we want to prove that for any natural number n is greater than or equal to 2, we want to show that the 1 minus 1 over root 2 times 1 minus 1 over root 3 all the way to 1 minus 1 over root n is less than 2 over n squared. Well, we'll want to show that, well, I won't go over the reasoning for this. Let's just go pretty quickly for this problem. So we want to show that so we want to have a lemma here. We call this a lemma. We want to, first we want to prove that for n that's greater than 2, we want to show that n is greater than or equal to root n plus 1. And the way we would do this is we would also have that, we know that n squared minus 2n plus 1, so this is n minus 1 squared, right, which is equal to n squared minus 2n plus 1 is greater than or equal to 0. And then we would have that n squared is greater than 2n minus 1. And then we would also have that this is equal to n plus n minus 1, right? Which is greater than or equal to n plus 2 minus 1, right? Because n is greater than or equal to 2, which is equal to n plus 1. So we have that n squared is greater than n plus 1. So we would also have that n is greater than the square root of n plus 1, right? Because remember that n is greater than or equal to 2, so we don't have to worry about like n is less than or equal to 1. Right, so now let's perform a variation on induction, right? So we know that first let's show that 1 minus 1 over root 2, right? Base case is less than 2 over n squared, right? So this is 1. Well, this is clearly true, right? So this is clearly true because 1 minus 1 over root 2 is clearly less than 1 because 1 over root 2 is greater than 0. Right, so now we assume that P of K is true, right? We assume that, so this is the inductive hypothesis. We assume that 1 minus 1 over root 2 times 1 minus 1 over root K is less than 2 over K squared, right? So we want to deduce P of K plus 1 from this. So essentially we have that the left-hand side, so the inductive step, we would want to prove that 1 minus 1 over 2 root 2 multiplied by all the way to 1 over 1 over root K plus 1 is is less than, 2 over K plus 1 squared, right? Sorry, that's sort of blurry. Oh wait, I just realized I messed something up. This is 2 over 4, right? Because it's n squared. So this would be equal to 1/2, right? And we can prove this by rationalizing the denominator. You get that this is equal to, I'll do this without proof, but you get that this is equal to 1 over 2 plus root 2, right? And that would be less than 1/2. You can basically do this by putting it all over root 2 and then multiplying both the numerator and denominator by root 2 plus 1. So instead of like rationalizing the denominator, you rationalize the numerator to get 1 in the numerator, you get 2 plus root 2 in the denominator. All right. Now let's continue. Sorry, am I going a little bit fast for this problem because we're running out of time. Next we would have that the left-hand side. So LHS of the inductive hypothesis times 1 over root k plus 1, right, is less than 2 over k squared times times this expression here, right? And then, right, and then we would have that this is equal to 2 over k squared times 1 minus 1 over root k plus 1. And then, well, you do a lot of algebraic manipulation. If I were to sum it up, you basically do the same thing. You try to rationalize the numerator and not the denominator. And eventually you get that this is less than, this is equal to 2 over k times, I'm skipping a lot of steps here, but this is equal to 2 over k plus 1 to k times k plus 1 plus k times the square root of k plus 1. And you get that this is less than or equal to 2 over k to the times k plus 1 plus root k plus 1 times root k plus 1. So this is where we used this lemma here, right? And then finally you get that this is equal to 2 over k plus 1 squared, right? And then you have proved the statement. Sorry I rushed this a lot, but we were out of time. So essentially for this problem, you would prove that you prove a lemma first because you use the lemma later on in the inductive process. And you notice that we had two inequalities here. So sometimes induction is a little bit more complicated especially for inequalities. All right, so we're out of time. I had two more examples prepared. You can take a look at them because they're all USMO questions, which means that they're on the AOPS website. So the first one is USAMO 2003. It's the first problem, and the second one is USAMO 2008. It's the first problem. You can look at these problems on the handout that's posted in the on the website. So thank you everyone for coming to all of these past lectures. It's been a pleasure working with everyone. So yeah, thank you everyone for coming. Heather, do you have any other comments?